Hello everyone and welcome to Cryptography 101. Today we're going to be talking about hashing algorithms. I'm going to give you guys a quick example real quick of something that might come up in day-to-day life or in the workforce. Then we'll talk a little bit about them. So let's say you have an important file to send someone and you want to ensure that it gets to them without any changes and in one piece. So you could use some trivial methods such as sending it multiple times or um, calling them to make sure that they got the same file you sent and nothing was changed about it. So, but the more efficient way to do that is a hashing algorithm. What is a hash? In short, a hash is a value that is a summary of all the information inside a document. So it takes a 60-page document, squeezes it until it becomes just an unreadable string, and in theory, it's impossible to restore without knowing the way it was used to be encrypted. So right here, we have a very simple example. So the input data is 1, 2, 3, 4, 5. The output data is 8061285. So the hashing algorithm would start. It would read the input, takes the input times 653, and then it writes in the input and it ends. So obviously on a more advanced hashing algorithm, it wouldn't just multiply by number, it would do some other crazy stuff. But this basically means it's infeasible to invert that and bring it back to its original state without knowing that it was multiplied by 653. So what makes the ideal hashing algorithm? Well, there are four things. The first of these is that it should be fast to compute. You don't want it taking too long, otherwise there's more efficient methods to use. A hash needs to be quick and effective. The second one, it needs to be impossible to remake the message for a hacker to get the message back just by reading the string. They would have to use a brute force attack and try a bunch of different things over and over to figure out what the original message was. It should have no collisions with any other hash. Each hash should be completely unique to the message, the information it is squeezing together. The last thing is every change in the message, even the smallest one, should change the hash value and be completely different. In the technology world, it's called the avalanche effect. So as you can see in this example, the word lion would become this random string of characters, whereas white lion would become a completely separate string of characters, nothing like the first. So then you take the W out of white lion, the height lion, and it's a completely different string of characters with no connection to the first. And then if you take the E off the end of white, it does it again. So this shows an example of the number 4. Every change in a message, even the smallest one, should change the hash value. And just a quick example here. So how would this be used in the real world? Well, going back to our example, we're sending a file to a friend. It's very important, and we want to be assured it's going to be received in one piece. That's where our hashing algorithm comes in. So in this example on the screen, you can see that user 1 sends user 2 the file, and does the file equal the received file? Are they the same? User 2 has no way of knowing. So right here is an example of how hashing algorithms would work when sending the file. So before sending the file, user 1 would use the hashing algorithm to make a checksum for the file, which is just a compressed form that it becomes. Then the user 1 would send it alongside the file itself. User 2 would receive the file and the checksum, and she'll use the exact same hashing algorithm that user 1 used on the file. And if she gets the same checksum that user 1 did, when she uses the hashing algorithm, she knows that the data in both the sent document and the received document are exactly the same. So this is how it'd be used in the real world. Because as we saw earlier, if you change even one letter of the hash, it changes the entire checksum. So, as cool as these are, there are some dangers to them. For example, because they're used so much, they can be, once they figure out how they're made, people can break them. An example of this is MD5. It was once considered very safe, and now it's completely compromised. It's so compromised that if you put the checksum into Google, it will give you exactly what that means. So that one has no safety anymore. This has also happened to SHA-1, and it will happen to SHA-2 someday, which was the follow-up to that. So in order to keep your data safe, you always want to use the safest. You always want to keep your security up to date, make sure it is safe. Okay everyone, thanks for watching my video. As always, it's been a joy. I'll see you next time.